I welcome all of you to our second part, that is lecture A4, where we are looking at cross products, moments, couples, and internal and external forces. I would just want to take you back. The first part, we looked at moments of a force about a point that was in 2D and in 3D. If you can remember very well, in 2D we used the scalar formation or the scalar analysis, where we are just multiplying the force times the perpendicular distance, which was d, for us to get that moment. But in terms of 3D, it is very difficult to use the scalar method. The easier way of solving those problems is by using the vector analysis. That is where I introduce to you the cross product, where I used a V was equals to a P cross Q, which is also the same as P times Q times sine theta. The theta, that is the angle between P and Q. Meanwhile, V is always supposed to be perpendicular to the plane. Note that always the V is supposed to be perpendicular to the plane, and that plane is where P and Q vectors are. We also discussed the internal and external forces, but the lecture only concentrated on the latter. Of course, that was the external forces. The internal forces will be looked at in the upcoming lectures. That is, I think, starting from lecture 6, 7, and 8. That's when you are going to understand, where you're going to analyze a structure starting from by using the external forces. After calculating the external forces, you come now to calculate the internal forces within a given member. In this lecture, we will look at, of course, moment of a force about a line or about an axis. We're also going to look at moments due to a couple and how to represent the same moment. We'll also look at resolution of a force into a force and a couple system. We'll of course look at the principle of moments. The first part, we also looked at the principles of transmissibility. This too is very much important for you to solve those problems, not only in lecture 4, but even the lectures, lecture 5, lecture 6, lecture 7, and so on. So you need to understand those principles. As earlier alluded, we looked at a moment of a force about a point. This time we are going to look at a moment of a force about an axis or a line, and of course the moment due to a couple. Now, the principles of moments. It states that the moment of a force about a point is equal to the sum of the moments of the components of that particular force about that point. The moment about a given point O of a resultant of several concurrent forces is equal to the sum of the moments of variant moments about the same. Here, what they were trying to explain was, this is A, then you have forces which are concurrent. You can see F1, F2, F3, F4. They are coming from A. For you to calculate the moment about those, you just have to have one position vector. Position vector multiplied, then you put in brackets your first force, second force, I don't know how many they are. You get the same moment. This is what this means. This is not supposed to confuse you. Another example. Determine the moment of the force about O. We are talking about O. You can solve this problem using two methods. One, you can use R, or you can use D. D, which is a perpendicular distance to where the force has been applied. When you want to use R, always know that your moment would be your R cross F. If you want to use a scalar method, it will always be your moment F D. It doesn't matter D F. Make sure that this D is perpendicular, which happens to be this guy, this distance. You are using a scalar method. Yeah, as I earlier indicated, there are three different ways of solving this problem. But these solutions that you can see here, they only used the scalar formulation. You can as well try to solve this problem using the vector analysis. For the scalar, the first example is where they calculated using a perpendicular distance D. The second one is whereby they introduced some components in the X and Y. This is along the Y, and this is along the X. And the other solution here, they just wrote, the axes were just turned by an angle to make it in a way that the line of the rod is parallel to the x-axis. You will still get the same answer. But find time and try to solve this problem using the cross product. Now, where you guys have got issues now, it's about getting a moment on a specific line or axis. If you got the principles just how to get a moment about a point, then it's supposed to be, it's not even supposed to make you confused. When you look at this R cross F, that is a cross product. But now we want to get along. We are not interested in getting any moment anywhere, but we just want to get the moment along a specific line. I explained about this. When you are removing a nut, those who have advantages of maybe removing a wheel from a vehicle, you realize that you don't need X, Z, and Y. You only need one axis, which is going to help you to remove your nut. This is what we are looking at. So in that case, when you look at the way this drawing is, we are all interested in the Y.
So we don't care about the x and z's. Once we do that, our nut will come out and our wheel will also come out. So don't make things complicated. I don't think they will help you. Just get it the way it is. When you want to get a moment about a line and axis, it will be a triple scalar product. There are two ways of doing it. If you want, you're going to do R cross F. You get that, that will be your moment. Once you have a moment, then you get your unity vector dot the moment. And how do we do that? You can remember very well. It's just multiply the I by the I, the X by the X, the Z by the X. As simple as.
This is example 4-9. Here, the example is just trying to apply the tools that you have obtained. Because here it's asking you the question to find a moment about A, to find a moment about a line which is AB, and also about the diagonal, which is also a line about AG. And it is also trying to make you guys think to determine the perpendicular distance between AG and the FC. You will realize that there is a relationship that is happening between the AG, which is this one, and the FC, which is that one. You will realize that there's a relationship, there's something that is happening in between those two lines. This example came as an exam, it also came as a test. So you really need to concentrate, to go through it and understand. Don't just memorize. First thing first, A, which is the moment about A, which is the moment about A. The first thing that we need to do, you first have to select your axis, X, Y, and Z. So when you look at this, here we have our I, which happens to be our X, and the J to be our Y, and the K to be our Z. It doesn't matter. You can even choose the Z to be the one which is vertical. But you just need to select, you need to choose the X, Y, and Z. Once you do that, if you can remember, the first thing that you need to do is to get the coordinates. So coordinates of A, when I look at coordinates of A, starting in the X, I think in the X is supposed to be 0. Then we got the Y, it's supposed to be positive A. Then in the Z, it's supposed to be positive A. Then you go to F, you get the coordinates of F. You'd want to get your position vector R, A, to where the force P is passing. So if you want, you can still use R, A to F, or R, A to C. You still get the same solution. How do you get the position vector? we always know that you need to subtract the coordinates, in this case, which is r f to a. You subtract the coordinates at f minus the coordinates at a. If you'd want to use your position vector from a to c, you still do the same. You subtract the coordinates in the x, y, and z. Subtract those at c and those at a. You have your r. But don't forget that you, at the end, you also need to get the magnitude. How do you get the magnitude? The magnitude, it will be the square root of that r. Once you do that, you now multiply your r over the magnitude times the force, which is p. Then you have a force vector like that, which is your p over square root of 2 multiplied by open bracket j minus k. Once you do that, you now apply your cross product, which is your r cross p. Don't forget on how to use or how to calculate the moment using the cross product. Can you remember how to calculate the determinant? If you can remember very well, here we need to have our I, here we need to have our j, here you need to have our k, instead of those unit vectors that you can see. Those unit vectors, they only work if you are using a triple scalar. That's when you can use those. But for now, for a cross product, we don't consider this. We're going to replace those with I, j, and k. Then if you want to find the component for I, you close that and that. Then it will be a matter of you multiplying that and that, which will be your r y times fz. If you'd want to calculate for the component in the j, you do the same. You close that and that. Then now it will be your rx times your fz, which will be that and that. Once you do that, you end up finding the moment about a, which is a times p over square root of 2 times open bracket the I plus j plus k. Moment about AB. Now, when you're talking about moment about AB, this is a line now. This is a line. This is where we apply the triple scalar. Now, since we already have the moment, which we are just from calculating, which is MA. It is just as good as doing a dot product, which is a unit vector along AB, which is the unit vector along AB dot the moment about A. If you'd want to do it the other way, you can still start from scratch by using this. The unit vector about AB dot the R cross F. You, at the end, you will find that is the correct answer. C, moment about AG, which happens to be the diagonal of that cube. AB, which is AG. The same procedure. Get coordinates of A, get coordinates of G. Once you have that, you subtract those coordinates at G minus those at A. You will find something like this. Once you do that, you want to find the magnitude. The magnitude of that AG, which is just a square root of A squared minus A squared and minus A squared. When you simplify that, you are going to find your magnitude to be that. Once you have that, you can remember that we also calculated the moment about A. So it's the same triple scalar that we are applying, because we have already calculated MA, right? The only thing that we are calculating is now the unit vector AG, which happens to be this. When you do your dot product, you find your moment about AG to be equal to a negative AP over square root 6. The alternative method is just by applying the triple scalar and use the determinant, you will still get the same solution. I know it might look complicated, but just find time. Go through it 1, 2, 3 times, then you are done. It will be part of you. Once you look at any engineering problem, whether 2D or 3D, you would know which tool am I supposed to use. Am I supposed to use dot product? Am I supposed to use a triple scalar? Am I supposed to use the cross product? For the last question, determine the perpendicular distance between AG and FC. The perpendicular distance, if you can remember how to calculate a moment using the scalar method, where we multiply the force times the perpendicular distance. Can you remember that? So that is the distance that we are talking about. But before we do that, the first thing that we need to do is to confirm that the force itself, which is P, and the unit vector, that is AG, if you do your dot product, P dot your unit vector, you get 0. When you get a 0, then you know that P is perpendicular to the diagonal AG. This is the logic. I mentioned this about dot product. So, if you do your dot product, then your final answer becomes to be 0, then you know that those two lines are perpendicular to each other. So, the first thing that you do, you confirm by doing a dot product a p dot the unit vector, you find 0, then you know that those two lines, the AG and the FC, are perpendicular. Now, since we have confirmed that the dot product is giving us 0, we go back now to our moment using the scalar method. If you want to find a moment is equals to the force times the perpendicular distance, which is d. So now we are looking for d, because we know that d is always supposed to be perpendicular, right? We already have the moment and we already have the f. The moment that I'm talking about is the moment about AG. Can you remember that we got the moment about AG, which was negative AP over root 6? So the only unknown is the d, the perpendicular distance. The only unknown there is d. We know our p and we know our moment about AG. You just change the subject, which is d. You'll find that your d is equals to
moment of a cup. I emphasize to tell you guys that a couple, this is a force that is, and there are always two of them, same magnitude but in different directions. How do we calculate a moment about a couple? Using a scalar method, the way you have this, you want to get a moment, forget about either this or that. You will just get a moment about that point, then you say moment is equals to, you have seen a d already, negative f d. I'm getting a moment about that. If you don't want, you can still do the same, get a moment about that. It will be a moment will be equals to, that will be now positive, because that guy is positive, f, and the same d, you are going to get the same, except in different angles depending on where you are getting the moment from. This is just an example showing you those who drive, those who have got advantages of driving a vehicle. When you are turning, maybe left or right, you would see that the tire will be turning. If you are turning left, you'll be turning left. Even your wheel will be doing the same. That is what you call as a cup. And I've tried to emphasize a couple does not mean anything else. Not a couple where people are married, no. Couple in engineering is something else. So you can see like what is happening here and what that guy is doing. The lever arm was 0.4 and the impact that he had put was 30, and they are telling that is equivalent to the same guy, except he had added more effort, but he had reduced the lever arm. So here we're just trying to show you how simple these things are. A couple, wherever it is, you can move it without any arguments. Here is a cup. I get a moment That will be, let me say I'm getting it from here. From here, it will be the D cross F. This is the one that I have here. I can take it wherever I want. I can bring it here. For as long as it's the same system, it doesn't change anything. Once it comes here, this moment it has got components in the X, in the Y, in the X, and in the Z.
Resolution of a force into a force at any arbitrary point, maybe let me say O and a couple. Force vector F can simply be moved to O by modifying its action on the body, if not along the line of action. Attaching equal and opposite force vector at O produces no net effect on the body. What this simply means is you have your force at this body, the force at A. If you'd want to move the force F to O, or maybe to O prime, the only thing that you need to do is you put two forces, same magnitude, but in opposite direction. What I mean here is, when you look at your force, which is this one, F, the first thing that you do, you apply two forces which have the same magnitude but opposite direction, which is this force and this negative force at O. What this means is the effect that this force F has on the body is still the same as when two equal and opposite forces have been applied. This is also the same as having a moment at O. If you take a moment about O, you realize that this is like a couple. This force and that force is like a couple. So when I calculate a moment about a couple, those two forces will end up as a moment, which is this. So what this means is, if you'd want to move your force, which was at A, to any arbitrary point, let me say O, what you need to do is you introduce two opposite forces with the same magnitude and change that couple system into a moment. You are going to have the same impact here and there. This also applies with changing your force from A to O prime. You are going to have the same force, but you would have introduced a couple moment. That's what it means. So the three forces may be replaced by an equivalent force vector and couple vector. This is what we call a force couple system. You might find certain problems, they are more complicated such that it will be difficult for you to solve those problems. You can use the resolution by simplifying the problem. Resolution of a force and a couple system into equivalent resultant force and couple moments. A system of several forces and couple moments acting on a body can be reduced to an equivalent single resultant force acting at an arbitrary point, an example maybe say O, and a resultant couple moment by using the famous equations, our famous equations. Fr, this happens to be the resultant force, is equal to summation of those forces. If it is a moment, if it is a resultant moment about O, will be equal to the summation of moments about O plus the couple moment. What this simply means is you have got two forces as an example. You have got F1 and F2. Applying our cross product, we need to have our R1 and R2. At the same time, we have a couple moment, which is M. You need to recall that this couple moment is a sliding vector. It is a sliding vector. So you can move it from point A to point B without changing any effect. So what this simply means is we calculate our moment, which is R1 cross F1, which is this. We do the same for the second force, which is F2, right? Since I've told you that this couple moment is a sliding vector, you just move it to O, which is this moment, right? There we have moment about O1, moment about O2, and the moment, the couple moment itself. Then also we have the first force and the second force. So the resultant would be this, where you are going to have our force, our resultant force, plus our moment. This moment, resultant moment, is a summation of the couple moment plus the moment 1, the moment 2. These are just tools that you can be using in making your solutions easier and faster. If you can remember these tools, instead of calculating, you start with F1, F2, moment. It will take time. But if you can apply these equations, Fr is equal to the summation of those forces, F1 and F2 as an example. The moment about R, about O, it will be equals to the summation of the moments about O. Those are the moment about F1 and the moment about F2. Then plus the couple moment. Example 4.10. Determine the resultant couple moment of the three couples acting on the plate as shown. Here, you have three couples. So the first one is this one and this one. The second one is this one and this one. The third one is this one and this one. The distance between the couples for the first one, it is 4 feet. For the second one, it is 3 feet. For the third one, it is 5 feet. How do we calculate a moment? Oh, we can remember that it is always the force times the perpendicular distance, right? Then the previous slide, I was teaching you on how to use these equations, summation of moments. But before you start doing your calculations, you need to agree on which signs are you going to use. But we agreed some time back saying that counterclockwise will be positive and clockwise would be negative. So when you apply those signs, you would find the first moment would be negative, the second one would be positive, and the third one would be negative. This is how you calculate. It's not even complicated, very simple. Example 4.11. Determine the couple moment acting on the pipe shown in the figure. Segment AB is directed 30 degrees below the XY plane. The first thing that we need to do is carefully look at the figure. What do you have and what don't you have? You have the force at A, which is 25 pounds, and you have another force at B, which is also 25 pounds. The distance between those two, it's 6 inches. We can get the coordinates at O, we can get the coordinates at A, we can get the coordinates at B. Already we know that that 25 pound is a couple. There are more than 3 ways of solving that problem. If you want, you can use the scalar analysis, where you just multiply the distance in between the couple, or you can as well use the vector analysis, where we first try to get the position vector from O up to B, or from O up to A. You get your position vector. Once you get your position vector, what is next? We now apply the cross product. Try to solve this problem using different ways. That is going to help you understand the whole concept of a couple, a moment, and how to calculate the moments. Here, the solutions are, the first one is of course using the vector analysis. And the second one is by using the scalar analysis. The scalar analysis is where you calculate the moment, that is, you calculate the force times the perpendicular distance. And for the vector analysis, this is where you apply the cross product. You can use either RA, you can use RAB, since we are looking at a couple. Example 4-12. Replace the two couples acting on the pipe column by a resultant couple moment. Here you need to apply those tools on how to replace a couple moment to a couple force system. Already we have a 150 couple, which is this one and this one, and we also have another 125, which is that one and that one. The distance between the first couple is 0.4 meters, and the distance between the 125 Newton couple is 0.3 meters. Take note that the pipe, it is at an angle where we have that triangle showing us 3, 4, 5. There are two ways of solving that problem. Using a scalar method or using the vector analysis. Vector analysis by using the cross product. Or if you want to use the scalar, is by calculating the moment by the perpendicular distance times the force. Then at the end, you do the summation of your forces, summation of your moments. The solution here is just showing us the first attempt was by using the scalar method. That is the first moment you multiplied the f times the distance, which is the 150 times the perpendicular distance, which is 0.4 meters, and you're going to get a 60 Newton meter. The second method is by using the cross product, which is first you get the position vector dc times the force, then you do your cross product. At the end, you know that you're going to have two moments, summation of moments m1 plus m2. I know it might be difficult, but find time to go through till you understand, till you get the principles.
When you look at this, it makes you, okay, let me just show you something. you have a 4 and a 3 and a 5. If we agree that this is the x and this is the y, right? These are angles, except you guys don't know that these are also angles. If I'm looking for a vertical component, which happens to be, in this case, a 4, whatever I'll be multiplying will be a 4 over a 5. This is a vertical component. When it's a horizontal component, I look for the horizontal component, which will be a 3 over a 5. Check when you get the angle in between this, you do your sine and cos. You will find the same what I'm just telling you. Here is the same principle. You can start from here, 200, you want to get your moment, that is 200 by 1, right? Then you get another moment, 1.25 times that, and this guy has got 2 components, the other one going there and the other one going there. The other one will be, when you add that, 1.25 plus 1.25, which happens to be the x component. Then the other guy, the y component. Then the x component, it will be just 1. Yeah, that will just be 1. Multiply times that. Then you get what you have there.
This is how we solve this problem. It is very much important for you to know the signs. So here is showing you the arrow facing the right is a positive, and the arrow going up is also the positive, and the opposite, it will be the negative. For the angles, as I was just explaining, for a component in the x-axis, because the x-axis is supposed to be horizontal, that is our x, and the vertical, that is our y, we just apply for the force in the x. It's just multiplying by the component which is horizontal, which is a 3 over the 5 times that force, which is the 500. You do the same for the force in the y, which will be the 4, because the 4 is vertical, over the 5 times the 500. All of us, we can remember on how to get the magnitude. All of us, we can remember on how to get the magnitude. Once we are done with that, then we use our moment summation, which is that. Always give the direction. We agreed that counterclockwise is positive. Counterclockwise, sorry for that. We agreed that counterclockwise is positive. Clockwise, negative. So in this case, this is supposed to be negative, as we agreed.
This is also the same principle where the question, very tricky, but if you don't see, sorry, maybe you need some special assistance. The structure member is subjected to a couple moment M. there's F1, F2. Replace this system by equivalent resultant force and couple moment acting at its base. The base is this one. How many forces do you have? And here you have got the other one that I even showed you, where there is a 3, 4, and 5. That is a triangle. We are done. That one we can sort it out the way it is. The problem that you might have is force 2. What is the problem with force 2? Because when you look at force 2, it's coming from the Z, then there is a 0.2 meter away from the Z axis. So get F2 to be making a force vector. How do you make a force vector? Already we know where this guy is. Here the coordinates we know, and where the guy is living we also know the coordinates. Get these coordinates, those are 0, 0, 0, 0, and where that guy the coordinates are in x is negative, if I can follow it nicely, it's negative 1.15. Then in the y is negative 0.1. Then in the z is 0. B coordinates in the x is negative. When I look at it, it's 0.15, comma. Then in the y, I look at it from the is positive 0.1, comma. In the z, it's 1. Then also get the coordinates for c. C in the x, I think is 0. In the y is also 0. Then z, 1, positive. Then you get your r. So once you have the coordinates for this, coordinates for that, even I'm even showing R, B, R, C, then you are done.
This is how we solve this problem. A force F1, it's supposed to be represented as in Cartesian notation. You do the same for the F2. Then you can apply now the moment summation. This, in fact, we discussed this in the first part of lecture F4. Then once you are done, then you do you use your determinants now, your I, J, and K. That's how it is. It might be, when you look at it, it might be complicated, but just find time to go through. You will get it and you understand. As earlier mentioned, go through these examples or go through these problems, these questions. They are coming from the recommended book, which is the 14th edition, Russell, 14th edition. Go through. Where you get stuck, we can find time. I go through, I try to to solve the problems, maybe in your, maybe we can have a Zoom meeting or something like that. I don't know, but just try to go through where you get stuck. You can tell the class rep concerning the same. I think this is the end of our lecture A4. The next one, it will be lecture A5. Lecture A5, yes, I'm going to introduce you new stuff, but lecture 1 up to this lecture A4, these are the foundations. This is the basic. If you don't understand these tools, then it will be very difficult for you to understand lecture A5, lecture A6, and so on. So you need to understand the tools. You need to understand this is the basic for CE2219, statics and introduction to strength of materials. So find time, go through, get the principles, try to solve the problems. Once you do that, then you are ready for lecture A5, lecture A6. I close here.